And we're talking about composition, decomposition, single replacement, and double. Reaction time. In the composition, A plus B goes to AB, and you have fewer components after the reaction is completed. In a decomp, you have more components after the reaction is completed. In a single replacement, a more active substance or element replaces a less active element and goes to AX plus B given off. In a double replacement, this is also known as an ion exchange and depends on the presence of a driving force pulling the reaction to completion, which we'll cover today. Okay, so that AX plus BY goes to AY plus BX. And on the product side, you don't have two driving forces, but you have, well, there's an exception, one exception. One of the components on that product side is the driving force. It pulls it to completion and prevents the reaction from reversing. Driving force is always on the product side. And results from the affinity of two ions. Like A has a high affinity for Y and would precipitate out of solution or leave the solution as a solid or become a weak electrolyte, we'll talk about today, or if we have time, and or be a gas decomposition. It's like Alka-Seltzer you used the other day in your water. It gave all bubbles. That CO2 coming up is a gas driving force that left the system and prevents the reaction from going in the opposite direction. So those are what we're focusing on. Now you should have an understanding of the first two right now. Is single replacement reactions. Single replacement reactions simply are oxidation reduction processes. Or in brief, redox. Some people use that extensively. And have an empirical form, A plus BX goes to AX plus B. And they depend upon what we call the activity series. When we talk about the activity series, we're talking about a collection of oxidation reactions that have ranked according to from most active to least active. And here is one I handed out to you. Hopefully you have that available. You can refer to it as we go through. But the top of this is the more active, and as you move down the list is less active. In a metathesis reaction, the rule is this. It's very simple. Whatever's at the top replaces anything below it. So lithium in here is the most active and replaces everything else in the process of a single replacement. You'll find it is the one that's of choice when making battery stuff, but that's another story. Potassium will replace everything under it, but will not replace lithium if you were running a single replacement. And come down into zinc will replace, say, copper, but copper will not replace zinc. So it's an order of priority in the activity series that you must No. Now, I'm not going to ask you to memorize that. You will learn which one, something about it, like the precious metals are always on the bottom of the activity series. Copper, silver, and gold are always at the bottom. And anyway, the others that are up here undergo oxidation very easily. They have few electrons in the outer shell, and they lose those electrons very easily. And so, as we go through here, I'll take magnesium, for example, and it's neutral. We can take solid form. It becomes it's a grayish-looking powder to ribbons you can polish to high luster. And we pick something like, I don't know, zinc chloride. I'd like that, and it has a form like this. Now, when I use it in aqueous form, AQ means it's in water and is in ionic form. In other words, it's cations and anions are floating around in solution. Well, when you put these together, magnesium being above the zinc, magnesium is, that's manganese. Magnesium's up here. Magnesium being above zinc, of course, magnesium will replace the zinc, and so we can write the magnesium chloride like that, and zinc will return to its basic standard state as a solid in neutral form like that. So the zinc will be replaced. I'm going to use that arrow around that context. I'd like to use it for something else. Now, as an oxidation-reduction reaction, as we indicated, these undergo changes in oxidation state. Use color. Magnesium in basic standard state, an element in basic standard state, has a zero oxidation state. Let me about 4 or 5 pages into your handout. And it's rules for oxidation numbers. Now, I'm not going to read these to you. As we go through and assign oxidation numbers, and you'll see it more when we do balancing using this method down here called the oxidation number method and balancing oxidation reduction reactions. But this is how you assign the rules for assigning oxidation numbers, and you are responsible for that. But as we go into it, you'll find it's very straightforward, and if you study it a little bit, you'll understand that. So when we look at this, that's a zero oxidation state. But here are compounds. Remember how we put compounds together? Sum of charges equals 0. Well, some of those elements in that compound are fixed charged elements. So chloride is a halogen. It's one of those fixed charge elements in the collection. So you recall the periodic, these are your halogens. They are all -1. So that should be group 1 +1, group 2 +2, halogens -1. So those are fixed charge elements in these. Oxygen, I told you to always a -2 unless I tell you different. And hydrogen's always a +1 until I tell you different. Okay? So this would be a -1. But you have 2 of them. So that's a -2 net charge. You have 1 zinc, so that has to be a +2 charge. So that's how you assign these oxidation numbers. Magnesium becomes a +2 charge, where chloride is a -1, and you have 2 of them, -2. -2 + 2 is 0. And so that confirms that compound. And zinc returns to basic standard state, and so it turns into a 0 oxidation state. Well, in the process of oxidation reduction, this gaining and losing electrons is the operative process. So we go with magnesium, and we put a bracket. This is one way to show this here. And I write in the bottom corner here a 0 going to a +2. So it's becoming more positive. That means you've lost electrons. This lost 2 electrons. And that is an oxidation process. On the other hand, zinc notice I put an arrow on the end of it. because we're going left to right in the reaction. Zinc starts as a +2, and when it is converted to basic standard state, it's neutral. It is zero charge. So how did I neutralize 2 plus charges? In other words, it has a surplus of protons in the nucleus, 2 protons. So I have to gain 2 electrons. And that process is called reduction. In all reactions, oxidation reduction reactions, you have 2 events that need to be occurring. A balance needs to occur. A balance of mass, of course, conservation of mass, and a balance of charge. So for all redox reactions, there is a balance of charge, balance charges, and balance mass. And so balance of charge is the number electrons lost. It must equal the number of electrons gained. So we see 2 electrons gained, 2 electrons lost in that reaction to illustrate that balance of charge. And then a balance of mass, of course, is the law of conservation of matter. Sum of the masses of the reactants equal sum the masses of the products. And so you have 2 events that need to occur in any oxidation reduction process. So half reactions can be illustrated with the electron, either an oxidation reaction or a reduction reaction. That's why they're called half reactions, because it's not all of the oxidation reduction process. It only shows either the oxidation or it shows only the reduction process. When you look at the activity series that I've given you and the handout, everything in this is shown as an oxidation reaction. That's an oxidation half reaction, because the electrons are shown on the product side in here. Now, if you want to illustrate the half reaction as a reduction, you just reverse it. You turn it around and show, say, chrome plus 3 electrons goes to chrome basic standard state, neutral form. Now, let's take aluminum solid plus, I don't know, I see chrome down there. Chrome plus 3, and we'll make it, put it in an aqueous for the, and it has a counter ion called a spectator ion. Okay, we'll get to that. It's not entering into the reaction, but we'll get to that later. And then it will go to aluminum plus 3, aqueous, and then the chrome will return to basic standard state like that. Now, if I want to illustrate the process that are taking place in using half reactions, I look at aluminum going to aluminum plus 3. Well, that process is losing 3 electrons, so I might write aluminum goes to aluminum plus 3 in aqueous medium in water plus 3 electrons. So that's an oxidation half reaction. But the reduction half reaction needs to be shown as gaining electrons. So I put the electrons on the reactant side this time. So I take chrome plus 3 aqueous plus 3 electrons goes to the basic standard state, and that's a reduction reaction, half reaction. And so you see how those are written. Now you can add those together such that but you can only add them together if the electrons cancel out. If, like, the 3 electrons on the left of the arrow will cancel out with the 3 electrons on the right of there, and you get what is called the net ionic equation. And so that's aluminum, as we've shown up here, plus the chrome, plus 3 aqueous, goes to aluminum, plus 3, the less active, plus chrome falls out as a solid. And this is the fundamentals of metallic plating. And if you're taking electroplating and you make one of the electrodes more active and will replace chrome, you have a chrome solution of salt, then the chrome will attach to whatever you have in the solution that undergoes reduction. Okay? That's called the cathode. Anyway, more complex reactions can also be done this way. Zoom it in for you. Okay. Standard electrode reduction potentials of aqueous solutions. Now notice up the top, it starts with lithium, just like your activity series. However, the one that I've given you is opposite of what this is. This is showing the ion gaining electrons and then going to the metal. That's why it's listed as a reduction potential table. But it functions in the same way that you would use the activity series table. Whatever's at the top will replace something at the bottom. And you can add those half reactions together. But the thing at the top is giving up electrons to something down here. So this is sending electrons downhill. So you take the one at the top and turn it around, okay, to show it as an oxidation. Just like we're showing the stuff at the top, and it goes oxidation, then you have to turn around the reduction bottom in the oxidation table. See, that's an oxidation table up there, like the one I handed out to you on the wall here. So you have to look at the reason it's an oxidation is because the electrons on the right of the arrows. The one in the reduction potential table, notice how the electrons are on the left. So if the electrons are on the left, what is that? That's a reduction. That's gaining electrons. Oil rig. Okay, so I can take calcium and react it with cadmium in here. I think there's 600 and some odd combinations of single replacements here. And all of them are electrolytic in nature. And so I could take any two reactions. Here's another, and it continues on the next page. There's a whole lot of stuff. And you have decreasing potential for oxidation. Okay, so the lithium end is the one that's giving off electrons. And the one below is the one gaining electrons. So if I take, I'll take some chrome plus 3. I'm just grabbing one in, and plus 3 electrons goes to, oh, obviously chrome. Okay. Thank you. There we go. That's an AQ. Right there, gains 3 electrons, chrome as a solid. Now let's say it's going to react with silver. Well, that's the reduction. It's going to react with silver. Okay, silver's at the bottom of this table, like that, plus 1 electron, and it goes to silver reduced state. Well, that's the way it's given in the tables, okay, as a couple of reduction reactions. But this chrome is higher on that table than is the silver. What that means is electrons are going to flow from that higher reaction down. Well, if that's the case, then this needs to be shown as an oxidation. So I'm going to rewrite this pairing, and I'm going to write chrome goes to chrome plus 3 aqueous as a solid. I put that in there. Like that. Plus 3 electrons, and then silver is going to be on the low end, it's going to be receiving. That means if it's receiving, it's reduction. So we're going to show that as a reduction reaction. Silver plus 1 aqueous plus 1 electron goes to silver reduced and comes out a solution, and that's called silver plating. I cannot add these two together in this form because the chrome half reaction has 3 electrons showing, and the silver has 1 electron. So you have the right to do anything to an equation as long as you do it to both sides. So you have the right to put a 3 in here and then rewrite it and have chrome going to chrome 3 plus 3 electrons, and then you have 3 silver ions, aqueous. You don't have to write the 1 up there, plus 3 electrons now. So you increase the number of electrons, and you get 3 silver atoms in reduced form, basic standard states. Now we have them at the same number. Now we've got a balance of charge. So I can now add those together and get the net reaction here. So that would be chrome plus 3 silvers goes to chrome plus 3 aqueous plus 3 silver in basic standard state. So that's how you deal with this. You can take either the reduction potential table and make the electrons balance, add them together. You've got a balanced oxidation reduction reaction. So that's one way to balance these things. And the ones at the top are delivering electrons down. Now you have to, if you're using the oxidation potential table, you have to realize that whatever's at the top will replace whatever's below it. But the way it's shown is an oxidation, so whatever's below, you got to turn around to show as a reduction. And so you have to get oriented with what you're looking at and understand oxidation reduction, how it is applied. So, in working with these, you will need your activity series, okay, and you will compare and using the activity series. Will calcium replace magnesium in this? Well, here's calcium right here. Move this up. Maybe I could get them all on there. Well, here's calcium and here's magnesium right here. So since calcium is above magnesium, a minute. There we go. Okay. So since calcium is above magnesium, yeah, it'll replace it. Now, when you write the outcome of this, you want to take calcium and hook it up with calcium chloride. But you don't, just because there's a 2 over here, now this one will be a subscript 2. But not necessarily always. What if you had calcium replacing silver? Okay, you'd have a silver chloride, then you would go to calcium chloride 2, and the silver would fall out as a precipitant. Anyway, this is a -1. Question? -1 and a +2. So I have to have 2 of them to balance out the charge to 0. That's what I'm trying to tell you. And yes, the reaction will take place, and magnesium will come out as a precipitating solid. It will be reduced form. So the oxidation reaction would be calcium going to calcium +2 electrons, and the magnesium reduction would be magnesium +2 going to magnesium, gaining 2 electrons and going to magnesium basic standard state. I need to put a neutral form right there. And you can go down through each one of these. There's aluminum and sulfur. Now this is where you would, aluminum and silver. So silver is way down there at the bottom of the activity series right here, and aluminum is pretty much up here at the top. So yes, aluminum will replace that silver. I'm going to write these out for you. Okay, let's take that aluminum as a solid, plus the silver sulfide, and that is in solution. So what's the outcome? Oh yeah, I'm sorry. I keep got it. Okay, the aluminum is going to replace the silver. We just saw the activity series, so we'll go to an aluminum sulfide, and the silver will come out in basic standard state. Okay, so that's a given. But how about the subscripts that would go into this? Well, aluminum is a fixed charge +3. Sulfur is a -2, and because it's an ionic compound, it follows the periodic table. Now, in molecular compounds, it may not. So we can put a 3 down here and a 2 down there, and so we have a balance of charge in that compound. Sum of charges equal 0. So we'll have to balance this out. Let's see. Wait a minute. Let me see something here. Yeah. Okay. So I need a couple of silvers here. I mean, aluminums, and then I need that's Ag2, so I need a couple here. And wait a minute, I got a 3 sulfur, so I got a problem here. So I got to have 3 there, 6. So I'm going to kick that up to a 6 now. And so I got 6 silver, 2 aluminums, 2 aluminums, 3. I got to have double that, so that's going to go to 4 ink. So now I've got 4 aluminums, 2, 3, 6, so 6 sulfurs, 2, 3. Well, that's inspection for you. Let me try that again. All right. That's the nature of the beast. Aluminum, 2 aluminums. Let's see what we can use here. Silver, sulfur. Well, let's find the sulfur here. 3. Let's start there. Get the silver. 2 and 3 is 6. I got 3 sulfurs. 3 sulfurs, 2 aluminums. Now we got it. Just takes a second sometimes. Get it together. Okay, so aluminum is going from here to here. Now, each element is to be taken into account first, and then you take the multiples. You hear what I said? Each element first, and then multiples. Each element goes, this one's going 0 to +3. So each aluminum is losing 3 electrons per atom. Well, we happen to have 2 of them in here, over here. So we have to have 2 over here. So really, what you have is 2 aluminums, each one losing 3 electrons. And this is a unique mindset. If you're going to work in chemistry, you're going to have to develop that. How to look at an oxidation reduction and think in terms of, well, how many of the elements are gaining electrons, how many are losing electrons. And in this case, you have 2 aluminums, each one losing 3 electrons. Okay? And the other oxidation state change, is what I'm trying to say, is in the silver. So each element of silver will start at a +1, because silver is a fixed charge +1, and goes to 0. So when you go from 1 to 0, that means that plus charge was neutralized. So it gains 1 electron. Gains 1 electron then. And so we have 2 silvers to start with, so we have to have 2 over here. Okay, but we have to have a total of 6 electrons. So actually it starts out with 2 silvers each. I'll show you how that, I usually do that. Yeah, start here. You got 2 silvers, each gaining 1 electron. So we'll need 2 silvers over there. That's what happens. So, but in order to balance this out, you will need to multiply that by a 3. So you have 6 total silvers over here, and this also multiplied by 3, and that becomes a 6. Now, before the day is over, hopefully you'll be able to do that, because we have a lot more to go in today's work on oxidation reduction. And it's not easy, guys. When you haven't done this before, I assure you it can be confusing, big time. Okay, now if we write it in half reactions, we start with aluminum is undergoing the oxidation side. We've already identified that. It's going to aluminum sulfide. Sulfurs are not spectator. So the aluminum is going to give up 3 electrons. I'm going to do it just in aluminum. Plus 3 goes into 3 electrons. I'm just going to do the 3 electron chains, show you for the individual ones. And then silver, each silver is going to gain an electron. 1 electron goes to silver neutral, like that. Okay, we can't add those together in this form, so I have to go through here with 3 and bring those up to 3 silvers. Okay, then I can add them together, and I'd have, well, we had 2 silvers in the beginning of this. Yeah, right here. So I got to use 2 more, and then 2 more. Let me move that down some. Plus 2 times 3 electrons goes to 2 times 3 silver right there. And this one has to balance with that, because you couldn't just ignore the 2 silvers here. You just can't ignore it. So that's why you have to start with that 2 silver in each one. So you have to increase it to 6. So I got to come in here with a 2 here and a 2 here and 2 times that. So we now have 2 aluminums. Yeah, it's confusing. 6 electrons, and then you have 6 silver ions plus 6 electrons, and that goes to 6 silver down here on the end. And you can add those together now, because you can cancel it out. We're not even close to the truth of what's going on here. So you got a couple of aluminums plus 6 silver ions going to 2 aluminum ions plus 6 silver elements falling out. Yeah, it's a handful. Well, we'll keep doing it. Right here, it says write the half reactions. That's what I'm trying to teach you a little bit about. So, we're given calcium as a solid plus magnesium chloride and an aqueous goes to something over here. And so we need to write the whole complete reaction first, and then identify oxidation reduction half reaction. So I'll take this and go to calcium. I'll move it over so I can have some room to put this together. Magnesium chloride, aqueous. And so this is 0, and this is a plus 2. Minus 1 goes to minus 2 overall. So if calcium replaces magnesium, it's going to hook up with the chloride like that. Okay, and then the magnesium is going to come out in basic standard state, neutral. It has to, all of them do. One replaces the other, if it's above the one that's falling out of solution. So, but is calcium chloride written in the proper format? No, because calcium is a plus 2. Chloride's a minus 1. And so I'm going to need 2 of those to balance the charge to 0. So, and then we balance it by, and that's aqueous. Then we balance it by mass. Now, to find the oxidation reduction, calcium goes to calcium plus 2. And magnesium goes to magnesium basic standard state, neutral. So we're at 0 going to a plus 2 here, and from a plus 2 to 0 here. So how does that translate? 0 to plus 2 is lost 2 electrons. So there's your oxidation reaction right there. And two positives are neutralized to 0, and so that's gain of 2 electrons. Well, that's convenient, but your charge transfer are equal. Anyway, so we'll take the calcium out, and it's going to lose, so we'll start with the solid going to the calcium ions, and that goes into solution as an ion floating around, plus 2 electrons. So there's your oxidation half reaction. Reduction half reaction needs to show magnesium gaining 2 electrons, so we'll write magnesium plus 2 aqueous plus 2 electrons going to magnesium basic standard state, and that's your reduction half reaction. And you can add those two together because of the charge balance. Cancel those out, and you have calcium plus magnesium plus 2 aqueous goes to calcium plus 2 aqueous plus magnesium solid. And that's called the net ionic reaction, or the net ionic equation. It shows the ions. The chloride in here is referred to as as a spectator ion. It's required because it's a counter ion to the metal, but it does not enter into the oxidation reduction process. We'll keep using that term later on in metathesis, probably more than this. And batteries are driven by oxidation reduction reactions between metals found in the activity series. Given the following metals, determine the activity series, from the activity series, which element undergoes oxidation and which element undergoes reduction, and write the related reactions. So when you have nickel and cadmium, you go into your activity series page and see the one that's on top replaces the one below. Well, what does that mean in terms of oxidation reduction? So if one at the top is undergoing oxidation, it's giving up electrons. It always gives up electrons. The one below is always undergoing reduction. Okay? It's gaining electrons. So you have to show it as that. It doesn't matter whether it's in a reduction potential table, and listen to me, a reduction potential table or an oxidation. Whatever's at the top of the reduction potential table or oxidation potential table will replace stuff below it. You just have to remember that the one that it's replacing, it always undergoes reduction. And the one that is doing the replacing is always going oxidation. It's losing an electron. So when we look at the nickel cadmium in here, back. Cadmium combination, we need to find the nickel cadmium in our activity series, which, remember, you're going to have this table attached to the exam, so you go back and look. So we'll see which one. And so we find nickel in here. Here's nickel, and where's cadmium? Cadmium is above it, so cadmium is the one that's going to replace nickel. So cadmium, nickel. So the one at the top is undergoing oxidation. Because it's going to be sending electrons toward the nickel, which is undergoing reduction. Like that. So now I need to show cadmium as an oxidation reaction. Cadmium, that would be cadmium metal, goes to cadmium, which will form they use plus 2 electrons. 2 electrons on the right of the arrow says oxidation, loss of electrons. Everybody good on that, I hope? And then nickel, being below cadmium, is undergoing reduction, so we show nickel plus 2 gaining 2 electrons, going to, well, I can spread it out. Goes to basic standard state, neutral form, as a solid. They're precipitating out or plating out. And that's your reduction reaction, half reaction. Because the electrons are on the left of the arrow. And so these will cancel, and now you can write cadmium. Typically the replacing element or the neutral standard state is given first. This is kind of a tradition. And then nickel plus 2 goes to the cadmium plus 2 plus nickel. And there's your net ionic equation. So you have to use the activity series to define it. Now, if we did that same problem using the reduction potential table, back to that for a second. See, we got cadmium and nickel. We got cadmium. Okay, so if you're looking in the reduction potential table, it shows cadmium above nickel, right there. And so in the process, something at top is undergoing oxidation. It's losing electrons. And so it's going to be sending electrons that way from cadmium to nickel. Well, if it's losing electrons on cadmium, you have to turn this reaction around. Well, in the in the activity series, you write it as given. See where the cadmium up here, you just write that one down because it's going to send electrons down here, but you have to turn this one around. That's what I'm trying to tell you. It doesn't matter which table it comes from. The one below is always undergoing reduction, and one at the top is always going oxidation. Well, sometimes it comes to you in an oxidation form, or sometimes it comes to you in a reduction form. You just have to apply the logic that goes with it. And then when you add them together, you get the net single replacement reaction is what it is. Okay? Okay, that